All right. 6.2. We're going to talk about calculating volumes now. So there are two methods that we typically use to calculate volumes in calculus. One way is to take slices of our three-dimensional object and find the area of each of those cross-sectional slices, and then integrate over the entire length of the volume that we're trying to find. You'll see what I mean as we go through this section. But we call this method the disk method or the washer method, depending on what you end up with. And this will make more sense. Again, this will make more sense as we look at some examples. The other way that we typically find volumes in calculus is to use what we call the shell method, and that'll be the topic of 6.3. But basically the idea behind the shell method is that instead of doing cross-sectional areas, you do cylindrical shells around your volume or around the solid that you're trying to calculate the volume of. And again, we'll talk in more detail about this when we get to 6.3. But for now, let's talk about volumes by slicing, disks and washers. So I'm actually going to start with an example that doesn't give you disks and washers, but it does illustrate what we're doing when we're finding volumes by slicing. To kind of give us some bearings, I guess. Let's say that you'd like to calculate the volume of some irregular solid like this, right? So certain volumes, like for cubes, it's like we know it's length times width times height, right? You don't need calculus for that. We have formulas for the areas of cones and spheres and all kinds of stuff. But when you have irregular shapes like this, what do? Well, what you could do is find the area of each cross section and then add those up. So just take thin slices, right? Take very, very thin slices, and what you basically have then is a two-dimensional object instead of a three-dimensional object. And you can find the area of that two-dimensional object if you're taking infinitesimally, I can't say that word. If you're taking really, really small slices, then it's basically a two-dimensional area. And then you can just add up all of those areas. In other words, you can integrate, right? Now, to find the area of each cross-section isn't hard because, again, we have calculus at our disposal. So we know that we can just use integration to find that area. So you find the area of each sort of two-dimensional cross-section and then add up all of those two-dimensional cross-sections to give you the three-dimensional volume. So in this case, what we'd get is a bunch of shapes like this of various sizes, right? Like down here, this shape would be small, and then on this end, this shape would be a little bit larger. But we find that the areas of each of those shapes, and then if A of x is that cross-sectional area at any point x along this length, then we just then the volume of the solid would be the integral of A of x dx. Okay. We could also integrate with respect to y if it's easier to do so, and I'll give you some examples of that as well. So just to show you what I mean by all this, like slicing and then adding up the cross-sectional areas that we get and stuff, let's look at some examples. So this first example says, find the volume of the right pyramid with height 3 inches and square base with 4-inch sides. Okay. So first of all, I'm going to draw a picture. And I'll use a pencil in case I have to erase. But let's draw a picture of this. And actually, I'm gonna draw this picture of this pyramid on a coordinate system, and I'm gonna choose where to place it so that actually this maybe I'll do and I'll draw the axes in black. Okay. Now, if it has 4-inch sides, then I'm going to center the cone, or not the cone, but the pyramid. I'm going to center the cone at 0. So if it has 4-inch sides, then that means I need to come out to 2. and then over to -2. And then it has a height of 3 inches, so I'm going to go up to 3. 1, 2, and 3. And then I'm going to try to draw this pyramid. So it's a three-dimensional object that I'm going to try to draw on here. But again, I'm centered. It's centered right here. So it might look something kind of like this, I guess. Right, so it's got a square base, so there's its square base, and then its height is 3. So I'm going to draw the point of the pyramid up there. So it's going to look kind of something like that. Maybe now that I've drawn it, maybe I'll color it in green so that it's a little easier to see. Okay, so we've got that pyramid. Now, we're going to want to slice up this pyramid and then calculate the area of each of those little tiny infinitesimal slices. Okay, so imagine. Well, first of all, you could slice this thing a whole bunch of different ways. You could slice it. Sort of starting at this corner and then slicing it this way. What you're going to get then is a bunch of, if you were to slice it like that, I think you'd get a bunch of triangles, right? You get a bunch of triangles. So that's one approach that we could take, and you're welcome to kind of try to figure that out if you'd like. I'm going to do it differently than that. I'm going to slice it vertically. So imagine that you take a little slice of this pyramid, right? So you get a little piece that looks maybe something like this. Where's the front of my pyramid? Oh, this is so it goes back kind of like that. Okay, so you get a piece that looks something like this, but it's going to be a square, right? It's going to be a square. So, and I can find the area of a square really easily. Right? I know it's a square because I've taken this slice kind of perpendicular to the y-axis, so I know that it's a square. But it's not a 4x4 square, right? Only the very base of the pyramid is 4x4. So this is some other measurement, and in order to find its area, I need to know what that side length is, because then the area of that square is just going to be, base times, or length times width, right? So let me redraw the picture so that I can get a better sense for what's going on. I'm just going to draw it two-dimensionally now. So I'm going to look at this front face of the triangle, right? So I've got a triangle, and then the square piece that I cut out was like this little cross section. Okay, and I want to figure out what this length is. Well, I know that the base of this triangle is 4, and I know that the height of the triangle is 3. And then let's not forget that ultimately what I want to do is I want to find the area of this square, but I also want to find just a general formula for the area of any square for any random cross-section, because then once I find that general formula, I'm going to want to integrate from the bottom to the top, right? So that I'm adding up all of those little tiny squares to give me the volume of the pyramid. So the bottom is at y = 0, and the top is at y equals 3. So I'm going to be integrating with respect to y, and so that means I'm going to want to figure out what this length is in terms of y. Well, so let's just say that from here to here, that this length here is y. Since I'm going to want to differentiate, integrate with respect to y, it would be good to label this y, the distance from 0 to wherever I've taken my cross-section. I'm just going to call that y. And then that means that this distance from here to here, well, it would have to be 3 minus y. Okay, now how does that help me find this side? Well, I can use similar triangles now, right? Because notice that this little triangle up here is similar to this big triangle down here. And that means that corresponding sides have equal ratios, right? So I can say something like, and by the way, maybe I'll call the length of this thing S. So maybe I'll call the length of my little cross section S. Okay, so I can say 3 minus y is to S. So the height of the triangle is to the base of the triangle, as the height of the big triangle is to the base of the big triangle. So 3 minus y is to S, as 3 is to 4. And now I can solve for S, right? So that I've got a way to describe the length of this square, right? So I've got a way to describe the length of the square in terms of y. Okay, so let's solve for S. If I multiply by S and then multiply by 3/4, I'm going to get S equals, or not multiply by 3/4, multiply by 4/3. I'm going to get S equals 4/3 times 3 minus y. Okay? Very good. So now I know that for any given cross section, the side length of the square of the resulting square is going to be 4/3 times 3 minus y, where y is the height from, or is the distance from 0 up to wherever your cross section was, right? That's good, because now I can say, okay, so the area of the square is base times height, or length times width, or whatever. So it's just side times side, right? It's just S squared. So that's going to be 16/9 times 3 minus y squared. Okay, so this is the area of just a random square cross section of this pyramid. This is going to be the area of that square. So if I can add up all of those areas, then I get the volume of the pyramid. Well, how do you do that? You integrate, right? We're going to integrate from 0 to 3. So we're going to integrate. So the volume is the integral from 0 to 3 of each of these areas, right? So 16/9 times 3 minus y squared dy. Okay, so we're integrating with respect to y. The setup is the hard part. The calculus is the easy part. So let's do this now, right? So first of all, I can take out the 16/9. Second of all, focusing on 3 minus y squared, you could do a little u substitution if you like, or you can go ahead and expand this and then use the power rule for each of the 3 terms that you're going to get. But let's just think. If I use the power rule, I'm going to add 1, so I'm going to get 3 minus y cubed, and then I have to multiply that by 1/3. But I also have this, it's a negative y in here, so if I make it negative 1/3, so here's what I'm thinking. I think I'm going to make this negative 1/3 times 3 minus y cubed, and evaluate from 0 to 3. Does that work? Let's see. If we were to differentiate, first we would use the power rule. 3 times negative 1/3 is negative 1 times 3 minus y squared, and then chain rule, so we would have to multiply by negative 1. The negative here will cancel the negative there and give us the original thing back. Okay, if that was too quick for you, just do a u substitution. You'll get to the same spot. Okay, now if we plug in 3, we get 0. So this is going to be 16/9 times 0. If we plug in 0, we get 3 cubed is 27. 27 divided by 3 is 9. So we get minus a negative 9. So that's just 16. Okay, so we get 16. I don't know why I put a check mark by it. I didn't check it or anything. You could check it though, right? If you know what the volume of a pyramid is. So the volume of a pyramid, I think, what is the volume for a pyramid? It's 1/3 of the volume of the corresponding prism. The prism would be length times width times height. Yeah, so the volume of this pyramid would be 1/3 times length times width times height, which is 3. And sure enough, right, 16. You might be thinking, like, well, why don't we just do it this way? Why do we do it the calculus way? Well, I just wanted to give you an example to show you that that this method does work, right? If you take a cross-sectional area, calculate the area, and then add up all of those cross-sectional areas, you get the volume, right? You get the volume, for sure. So, well, let's do another example. This example is going to be an actual disk method example. So this is more like what your homework problems are going to be like. It says, find the volume of the solid that is obtained when the region under the curve y equals square root of x over the interval 1, 4 is revolved around the x-axis. So we call these things solids of revolution because you're revolving them around some axis. It doesn't have to be the x-axis, and we'll see some other examples. But solids of revolution are always going to yield these circular cross-sections. And so what you end up with are basically a bunch of disks. So you find the area of all the disks, add up all of those areas, and then you get the volume. And that's why this is called the disk method, right? Or the washer method. We'll see some washers as well in a second. But let's do the disk method on this thing. Now the first step is always draw a picture, right? Just draw a picture. It's going to be, it's going to make, if you don't draw a picture, you're not going to have an understanding of what's going on in the problem. So let's draw a picture here. So let's see. So first of all, I think it's a good idea to just draw a picture of the region before you try to draw like the three-dimensional solid that's being described. Just draw a picture of the region. So we're interested in the region on the interval from 1 to 4. So 1, 2, 3, 4. And it's the region under the curve y equals square root of x. So square root of x starts at 0, and then it goes up to 1, 1. And then it goes up to 4, 2. So it looks like the curve we're looking at is something like that. And the region that we're looking at is this region right here. Okay? But we're going to take this region and revolve it around the x-axis. So we're going to take it, we're going to revolve it around the x-axis, right? So what do we get when we do that? We're going to get a picture that looks so 1, 2, 3, 4. If we revolve it around the x-axis, it's going to be mirrored kind of this way, right? Oh, that was poor. That was poorly done. Good thing I'm using a pencil. Okay, so you get something like this, and you're revolving it this way, right? Yeah. So this is the picture that you get, right? When you revolve it around the x-axis. So this is some solid piece. So I guess you wouldn't actually be able to see. You wouldn't be able to see this. It would be behind the solid that we're looking at, right? So actually, this is kind of the picture that you get, right? So you wouldn't be able to see that part, but yeah. So this is the picture. So if you do the same thing that we did in example 1, and you start to, where you start to slice it up to get one-dimensional areas. So if we take some like random slice of this thing, at some random point, you can see that it's going to be a circle, right? So the question is, what's the area of that circle? Well, the area of a circle is pi r squared. We need an expression for the radius r. Well, if this is r, well, not r, but let's say if this is x, then the radius is the function value right here, right? This is square root of x, right? Y equals square root of x. Or maybe I'll say it's the point x square root of x, right? This is square root of x over here. But anyway, that tells you that the radius is going to be square root of x. And the same thing if you take a cross section over here, right? The height is still square root of x. So the radius is still square root of x. So the radius is just square root of x anywhere you take a cross section. So the area of any of these cross-sectional circles is just going to be pi times square root of x squared, or in other words, pi times x. So that's good. So we know that the cross-sectional area of the cross-sectional area at any point x is going to be pi times x. So then we can find the volume of this solid by just integrating from 1 to 4. Integrating this area from 1 to 4. So the volume is going to be the integral from 1 to 4 of pi times x dx. Okay, so that's pi times x squared over 2, evaluated from 1 to 4. So that's going to be, if we plug in 4, we get 16. 16 divided by 2 is 8, so we get 8 pi. Minus, if we plug in 1, we get 1/2. So we get 8 pi minus pi over 2. So that's 16 pi over 2 minus pi over 2, so 15 pi over 2. That's our final answer. And there you go, right? That's the volume of that solid. So this is how these kinds of problems go, and this is why it's called the disk method, because you get all these disks whenever you take a cross-sectional slice. You get the result is a disk, or sometimes a washer, right? Sometimes it's a washer. So let's look at another example. Okay, so this one says find the volume of the solid generated when the region enclosed by y equals x squared, or y equals square root of x, y equals 2, and x equals 0 is revolved around the y-axis. Okay, so same function, square root of x, but this time we're revolving it around the y-axis, and we have some other kind of boundaries, I guess. So again, I'm going to start off by drawing a picture of the region in question, and then I'll try to figure out what it looks like when I revolve it. X equals 0, y equals 2, and y equals square root of x. So square root of x goes through 0, 0, 1, 1, 4, 2. So there's square root of x. Okay, x equals 0 is just the y-axis. Y equals 2 is this line right here. So the region enclosed by those three curves is this guy. And we want to take that and revolve it around the y-axis. We want to spin it. Whoops. That wasn't done very well. Let me try again. But we want to spin it around the y-axis. Okay? So let's see what we get. So I think we're going to end up with something along these lines. So 1, 2, 3, 4. 1, 2, 3, 4. 1, 2. And I think it's going to go something kind of like this, where we've got so it's gonna be this almost like a cone looking thing, right? When we do the revolutions. Okay, I could have done a better job. Let me redo it in pen. But yeah. I don't know if this is any better as it turns out, but hopefully you get the idea. Right? There's the solid that we get. Now, if we slice, if we take vertical slices like we did on the last problem, notice that we're not going to get circles. Like if I take a vertical slice here, I'm going to get this weird looking like kind of shape, right? But it's definitely not a circle, right? It's not a circle. And in fact, I don't know how to calculate the area of that. So I don't want to do that. But notice that if we take horizontal slices, well, then we do get circles, right? Like if I take a slice here, I'm going to get this circle, right? Like if I slice it right there, or if I slice it right here, I'm going to get this circle, right? So I'm just going to get a bunch of circles if I slice it up horizontally. So that tells me that I'm going to be integrating with respect to y. And well, what do I need? I need to know the area of those disks. So the area is going to be pi times r squared. Now, what is r? What's the radius? Well, the radius is the distance from here to here, right? In other words, it's just the x coordinate, right? It's just the x coordinate. But I need that x coordinate in terms of, because since I'm going to be integrating with respect to y, I need the x coordinate in terms of y. So I don't just want to call it x. I need to take y equals square root of x and solve it for x. So I'm going to get x equals y squared. So for any given y value, the radius is going to be y squared, right? So I'm going to get y squared squared. So the area is pi times y to the 4th power. And now I can find the volume pretty easily, right? The volume is going to be the integral from 1 to 2, right? We went from 1 to 2. So it's going to be the integral from 1 to 2 of the area pi y to the 4th dy. Okay, that's not terrible. This is going to be pi times y to the 5th over 5, evaluated from 1 to 2. If we plug in 2, we get, I think, 32. 2 to the 5th power is 32. 32 over 5. So we get 32 pi over 5. And then if we plug in 1, we just get 1/5. So we get minus pi over 5. So that seems like we're going to get 31 pi over 5 as our final area there. Oh, except that I should be integrating from 0 to 2, right? Why did I say 1? Why did I say 1? It should be 0. If I plug in 0, of course, that's just 0 over 5. So I should actually just get 32 pi over 5. My apologies. I'm not sure why I said I was integrating from 1 to 2. I'm integrating from 0 to 2, right? From 0 to 2. I think I said that, and then I wrote down 1 for some reason. Anyway, so that's that one. So as you can see, right, this disk method, it works whether we're taking vertical slices. If you're taking vertical slices, then you're integrating with respect to x. Your function needs to be in terms of x. Your limits of integration are along the x-axis, right? And you're taking these vertical slices. Or it works if you take horizontal slices. And if you take horizontal slices, that's perfectly fine. But then your function needs to be in terms of y, and your limits of integration need to be along the y-axis. Okay. I have two more examples that I want to show you in this section. So this first one says, find the volume of the solid generated when the region between f of x equals 1/2 plus x squared and g of x equals x over 0, 2 is revolved about the x-axis. Okay. Well, let's draw this thing. 1/2 plus x squared. How odd. Who chose this example? I did. I chose this example. Well, let's see. So we're integrating from 0 to 2. Okay, so I suspect I'm not sure that I needed an x-axis quite that large, but anyway, 1, 2. Oh, maybe I'll say 1, 2, 3, 4. Okay, so for the x squared. But anyway, g of x equals x. Gonna look something like that, right? That one's easy. F of x equals 1/2 plus x squared. So this is just a parabola, but it's been shifted up half a unit. So it kind of starts there. And then we go to 1, 1.5. And then we go to 2, 4.5. So like all the way up here, I suppose. But anyway, it's going to look something like that. And then we're only interested between 0 and 2. So we get this kind of odd looking shape, which I feel like I didn't draw very well, but that's okay. We're going to redraw it in a second, because we want to take this thing, and we want to revolve it around the x-axis. Okay, so if you imagine taking this and spinning it around the x-axis, what do you get? Well, let's see. So you get something like this. Boom, boom, and boom. And boom, boom. And then the same thing going down the other way. And one, we'll say this, this, and this. So something like that. And makes this kind of a shape. So it makes almost this kind of weird cone type of shape, I guess. It's this really weird kind of cone type of thing, right? Okay. Well, vertical slices are going to be the way to go here. If we take horizontal slices, we're not going to get circles. We're going to get these really weird shapes. But if we take vertical slices, we're going to get a bunch of circles. But notice that they're not discs, because actually what we have is like this thing, right? The center part is empty, right? It's like this hole in it, right? Because it's all this empty space down here. You took this and you revolved it around, you get a bunch of empty space in the middle. This is the empty space in the middle. So so if you take a cross-sectional cut of this thing, you're gonna get a washer, right? You're gonna get a washer. You know, if you were looking at it head on, I guess, like if you're looking directly kind of perpendicular, you know, it would just look like a washer, right? Just look like this washer. Okay. Well, okay, good. So now how do we find the area of that washer? Well, if we find the area of the big circle and then subtract off the area of the little circle, well, then we'll have the area of the washer, right? So what's the area of the big circle? Well, that's going to be pi times r. What's r? It's the distance from the x-axis to the function value of this top function. The top function being 1/2 plus x squared. So it's going to be r 1/2 plus x squared squared, right? So that's the area of the big circle, but then we have to subtract off the area of the little circle. So let's say minus pi times r. What's the radius for the little circle? Well, it's this function value. This function value is just x. So r squared. Okay, we can simplify that a little bit. So we can say area is going to be, first of all, I can factor out a pi. Second of all, I can expand this thing. 1/2 plus x squared squared. So if you square this binomial, you're going to get 1/4 1/2 x squared twice. So you're just going to get 1/2 x squared plus 1/2 x squared. That's just going to be x squared. And then x squared squared is x to the 4th. And then you're going to subtract off another x squared. Oh, that's pretty nice, actually. So this gives you pi times x to the 4th plus 1/4. So each cross-sectional washer is going to have area pi times x to the 4th plus 1/4. So to find the volume of this weird cone type of thing, we just integrate. Right? So the volume is going to be the integral from 0 to 2, right? From 0 to 2 of pi times x to the 4th plus 1/4. Okay, so that's pi times x to the 5th over 5 plus 1/4 x, evaluated from 0 to 2. So that's pi times 2 to the 5th is 32. 32 divided by 5 is, well, 32 over 5. 1/4 times 2 is 1/2. And then when we plug in 0, we're just going to get 0. Okay, so 32 over 5 plus 1/2. How much is that? Let's see. I don't feel like doing the math in my head. 32 over 5 plus 1/2 is 69/10. So we're going to get 69 pi over 10 as our final answer, right? So that's the volume of that crazy looking thing. So it's interesting. Sorry. I was just looking at the example in the book to make sure that I got the same answer as they did, but I was looking at the wrong exercise, and I was like, wait, why did I get something different? But no, 69 pi over 10. Yep, that's correct. Okay, good. 69 pi over 10. Moving on. Okay, last example in this section. So this one says, find the volume of the solid generated when the region under the curve y equals x squared over 0, 2 is rotated about the line y equals -1. So this is an interesting example because so far all of the examples that we've seen, we've been rotating around the x-axis or the y-axis. But this just goes to show you that the axis of rotation could be any line, right? It could be any line. So this time, let's revolve around the line y equals -1. Let's see what's going on here. So y equals x squared, right? Like something like that. We're interested in the region under the curve. So when they say under the curve, they mean between the curve and the x-axis. So they're talking about this region here. That's easy enough. But now they want us to rotate this about the line y equals -1. So the line y equals -1, that would be this line down here. I don't know why I'm having such a hard time drawing that straight line. Let me try again. Okay, so that's the axis of rotation that they want us to rotate around. So we're supposed to rotate around this thing. What do we get if we do that? Well, I think what we're going to get is we're going to rotate this around, and we're going to end up kind of like down here. Right? And there's going to be a gap. So I think -1, and then -2, and then all the way down to -6 is probably where I need to go along the y-axis. 2, 3, 4, 5, 6, right? So here's my axis of rotation. 1, 2. So I've got this set up there. Then I'm going to have 1, 2, 3, 4. Yeah, this set up here. Okay. Hold on a second. Let me see if I can. Okay, so my axis of rotation. It's just this thing, though. Oh, I see. Yeah, okay. So it's this. It's this, right? So I've got this kind of empty hole there and there. And then I've got a bigger hole, kind of like that. Yes, there. That's what this thing looks like. So this is another washer type of thing, right? So this is another washer. Okay. So let's see if we can figure out the area of this washer. So it's going to be pi. Well, it's going to be the area of the big circle minus the area of the small circle. Area of the big circle is going to be pi times r. What's the radius? Well, the function value here is x squared, right? For any given cross-section, it's going to be x squared, but then plus 1, right? Plus 1, because the center of the big circle is actually down here at -1. So you have to say x squared and then plus 1 to get that radius. You're going to say, so the radius is x squared plus 1 squared. So that's the area of the big circle. Then we have to subtract off the area of the small circle. That's going to be pi times, what's the area of the small circle? Well, the radius here is just 1. It's always going to be just a fixed 1, right? So pi times radius squared. Right? Area, again, radius of that little circle is going to be 1. No matter where you take your cross-section, right? So even if you take this cross-section, the corresponding washer that you get is still going to have radius 1. The big circle is going to still have radius x squared plus 1. The little circle is going to be just 1, right? All the way through. Okay, good. So I'm going to factor out a pi. I'm going to expand this, get x to the 4th plus 2x squared plus 1, and then 1 squared is 1, so minus 1. Okay, so the area looks like it's going to be pi times x to the 4th plus 2x squared. Okay, that's the hard part. The integration is easy, right? So to integrate this now, we're just going to integrate from 0 to 2. We're going to integrate the area from 0 to 2. So the volume is going to be the integral from 0 to 2 of each of those cross-sectional areas. Plus 2x squared dx. Okay, so I can factor out that pi. I'm going to have x to the 5th over 5. Why do we always end up with x to the 5th over 5? And then we're going to have 2x cubed over 3. And we're going to evaluate that from 0 to 2. So I plug in 2, I get 32. Here I get 8 times 2 is 16. And then if I plug in 0, I get 0 plus 0. Okay. Let's see now. 32 fifths plus 16 thirds is 176 over 15. So that our final answer is going to be 176 pi over 15. Okay? Okay, so washers, right? Washer, washer, and then the other things were just solid discs, right? Okay, so that's the disc and washer method, and that's all I have to say about 6.2.